Okay, study people, I'm here to help you again. Exam 3 review. Next problem, number 5. Draw the shear moment diagram. My favorite thing for the given load, okay? Before we get going, remember the order of the lines for shear moment diagram problems. If you have a concentrated load, the next graph down is going to have a distributed load. The next graph down from that is going to have a slope, and the next one down from that is going to have parabolic and then cubic, okay? The order of the lines. As you go down, depending on what you have, that's how they're... So this one, next graph down is going to have that one. The next graph down is going to be that one, right? This one is that one. Next graph down is going to be that one, and so on and so forth, right? That works every time. So, what in the world do we have here? We have a beam with a distributed load on it, and it's got some other junk on it over there. It's got a pin connection in the middle, and then a lot of other stuff. There's a lot of stuff going on here, right? Now, there is no forces in the x direction, so AX is going to be 0. I'm not going to draw him, but I'll draw this. There's an AY there. There's a BY here, and over here, there's a CY. Okay? Now, to find global equilibrium, I'm going to tell you right now, there is way too much stuff on this beam. Way too much stuff. So what are we going to do? We're going to take it apart, aren't we? Let's take this beam apart. It's a frame problem, isn't it? Okay, and let's see if we can find this global equilibrium before we do our shear moment diagram. Okay, so here comes global equilibrium at you. I'm going to divide this into two parts. Here is this beam section here, okay? And then I'm going to draw this beam section over here, All right, let's put some forces on this and see if we can figure out what's going on. Okay, so this guy's got AY here. He's got BY over here. Now, what you should be doing right now is you should be pushing pause, and you should be trying to do this with me, okay? Because watching me do this is not going to make you any better. You got to practice this. So you should be pushing pause right now, doing this, and then coming back. Are you back? Did you do it? No, do it. Push pause. Okay, come on, let's go. Here we go. All right, it's got a distributed load up here on top. Okay, and that distributed load is, what is it? 3 kilonewtons per meter over 15 meters. 3 times 15 is 45. So that's the same as a distributed load of 45 kilonewtons. Same as a concentrated load of 45 kilonewtons. And then over here, D, well, I've got a pin connection. Now, I already know that AX over here is 0. So that means that DX, which is here, that guy's got to be 0. Which way is that going to go? I don't know. I don't know. I might have to guess, right? I might have to guess. So I could guess dy is going down. And it doesn't even matter, does it? If I get it wrong, I'll just get a negative. That's no big deal, okay? But here's what I can't do. I can't guess that down and that down. They got to be opposite directions. That's a must, okay? And then I've got over here, 15 kilonewtons. And then a burrito force over here. Look at that. That's 25 kilonewton meters. And then I got a CY over at the end. CY. Okay? So where are you going to start? Where are you going to start over here? A lot of unknowns. I think we better start over there. Let's start over there and do the moment at D. Okay? And let's see what we get. If I take the moment at D, I get 15, which rotates me positive. So 15 times how far away from D is that 15? I don't know. You didn't tell me. It's halfway, okay? I'm sorry. I'm sorry. No, this is 4 meters. And this is 2 meters, okay? Sorry. Not sorry. Okay, the 15 is 4 meters away. Okay? And then there's a burrito force, and we just put him in our moment equation. I drew him negative, so minus 25. And then CY rotates me positive, so plus, oh wait, the 15 also rotates me negative, doesn't it? Man, I'm messing up. CY times 6. Okay, so let's see what CY is there. Calculator, where? It's back pocket calculator. Here we go. Okay, on. 15 times 4 plus 25 equals 85, and then divided by 6 equals 14.17. So CY 14.17. Okay, and that's kilonewtons. Okay, guess what? This is 15 going down, that's 14, so I assume this is the right direction, miraculously. So 15 minus answer equals 0.833. Okay, not a lot, but there's a little bit over there at dy. It's 0.833 kilonewtons. Okay, now what? Take the moment at A, and I get 45, which rotates me positive, so 45 times how far away? It's half of 15, 7.5, and then BY rotates me, oh, this one's negative. That's, I get my directions backwards, that's negative. BY rotates me positive, so plus BY times, let's see, how far? 12. Okay, and then dy again, rotating me negative over here, minus 0.833 times 15. Okay. Whew. Okay, so, yeah, that's right. So what do we get here? 45 times 7.5 plus 0.833 times 15 equals 350. So BY equals 350. 350? Oh, dadgummit, I've got to divide that by 12, don't I? I was like, that's too big. How about 29.17? Does that sound better? That was going to be a lot, wasn't it? 29.17 kilonewtons. Okay? So what does that make AY over here? Total down stuff got to equal total up stuff. That's going down, so minus 45 leaves me with 15.83. Okay, so there you go. There's all my global, all done. Okay? So AY is 15.83. BY is 29.17. Okay, these are kilonewtons. And then finally, CY is, where is CY? We found him, 14.17. Do we care what's going on at D? The answer is no, because it goes down 0.833 and then it goes up at the same point, 0.833. So the sum of the moments at D is 0. Okay? So that, my friends, is how you do global equilibrium. That was a Chapter 6 frame problem right there. Before we ever do the shear moment diagram, we just did a Chapter 6 frame problem. That seems... Okay, did you catch me what I did wrong in that last step? I messed up. When I added the sum of the force and the y in that last step, I forgot about that 0.833 over there on the end. So I added that, which makes AY really 16.67, not 15.17 or whatever I had there. That wasn't right. Okay, so we got it fixed. Thank goodness, okay? So here we go. We're going to do our MV diagram. So if you start this at the top of the page, because all these things are related, right? You don't want to run out of room here. Here's what we're going to get, okay? Let's, we're going to draw some. There's our V diagram. There's our M diagram. V, M. V is in kilonewtons, and M is in kilonewton meters. Okay? So we're going to put on here our discontinuities. That's everywhere we think something interesting is going to happen. I think something interesting is going to happen here. Okay? And I think something interesting is going to happen here. But not because there's a pin connection there, but because that's the end of the distributed load. Okay? I think something definitely interesting is going to happen there. And then something interesting happens over here at the end of the beam, okay? Now you'll notice one thing. I have subdivided this total load here, this distributed load, into two parts. The part up to point B, right, which is 12 times 3, which is 36. And then the part after point B, which is 3 times 3, which is 9. So why did you do that? Well, as I'm graphing this, what's going to happen? I'm going to go down, but right in the middle of that graph, I'm going to have a jump force here, right, a Van Halen force. And I'm going to have to jump up and then continue going down some more. So I got to fix that, don't I? Okay. Let's see what's going on. All right. So you start off at 0. Let's do it in another color so you can see it good. Let's see what I get out of my pocket. Do I get a, where's a blue one? Where's a blue pen? How many pens do you have in your pocket? Here's a blue one. All right. Here we go. So the first thing I'm going to do, you remember our load backpack. We're going to put on our load backpack. It's all empty. We hop up on the beam, right? First thing we get is 16.67 up. So here we go. That takes us to right there. 16.67, okay? Now remember to put your units on your graph. That way you don't have to put any units out on your thing and you get on your diagram and you won't get points off for having no units here, okay? So here we go. So we're going to go down. How much are we going to go down? Well, from here to the next thing that happens, I'm going to go down 36, right? Because I take a step, I go down 3. Another step, another 3. Another step, another 3. So I'm going down like that, right? And remember from the order of the lines, this one's straight across. So the next line down is going to be a slope, okay? So we're at 16.67. Oh, that's not right. 16.67. And then we're going to go down 36, which takes us to negative 19.33. Okay, that's right there. Negative 19.33. And how do we get there? Well, we get there using a straight line, don't we? That's pretty straight. Okay, then we got to go up. Bam! Another Van Halen force makes us jump 29.17. So plus 29.17 equals 9.84. Okay, so there we are at 9.84. Okay, and we go like this, don't we? Straight up. Now what? Now we go down another 9, which puts us at 0.8, if we want to be specific, 833. Okay, how do I know it's 0.833? Do you remember what V was when we solved for it at that pin right there? I mean, there's a little bit of rounding going on here, right? I got to be careful with the rounding, right? I rounded that. So, but I know what it's got to be. It's got to be 0.833, doesn't it? You can call it 0.84. It's okay. It's okay. And then what? No change, no change, no change. Bam! What happens right there? Somebody put 15 in my backpack, right? So that's going to take me downhill to there, which is negative 14.17. And then no change, no change, no change. And then John Denver force right over there. Take me home to the place I belong on my shear graph back to 0. Okay, that's silly. Here we go. Let's put some pluses and minuses in here. Plus, minus, plus, plus, minus, right? And that just tells me the slope on this next graph. So it's going to go uphill, downhill, uphill, uphill, downhill for down here, right? Okay. Can we use the graphic method? Did we have a parabolic curve cross this axis? No, we did not. So we can totally use the graphic method. Now, one thing I don't know is I don't know what that distance right there is. I'm going to call it X, okay? I don't know what that is. I don't know how to find that. Well, how about this? Similar triangles, okay? So you got a big triangle here is to the little triangle, right? So here we go. 12, right? The big triangle is 12 is to, what was that total distance? 36, as X is to 16.67, right? So let's see, 12 divided by 36 equals times 16.67 equals 5.56. Okay, so this distance right here is 5.56 meters, which means that this distance over here is minus 12, 6.44 meters. Why did I need to know that? Well, because the graphic method uses the areas of these shapes, and so I need 1/2 base times height to figure that triangle, don't I? So here we go. 1/2 base times height. So 16.67 times 5.56 equals divided by 2 equals 46.34. Okay, there's that one. This one, 6.44 times 19.33 equals divided by 2 equals 62.24. That's that area. Okay, what about this area? It's two different shapes. It's 3 times 0.833, so 3 times 0.833 equals 2.5. This little bit down here is 2.5, and then that little triangle there is, I forgot, it's 9. 9 times 3 equals 27 divided by 2 equals 13.5, and 13.5 plus 2.5 means that this area here is 16. Okay, very nice. Now we're on to the next little shape over here. 0.833 times, how big is that? 4. 3.33. And finally, the last little shape over there is 14.17 times 2, 28.34. All right. So I've just calculated the areas of all of those shapes, because remember, the area, width is in meters, height is in kilonewtons, and so the area of that shape is in kilonewton meters, which is, boom, one of these. Now I have done this. Where this crosses the axis, I have a new interesting point down here, because my graph is going to go from uphill to downhill, so I'm going to have a humpy-do on my graph, right? A local min or max. Okay? So here we go. We're going to start off at 0. We're going to go uphill 46.34. So there it is right there, 46.34. How do I get there? Okay? This line is a straight slope. The next one down, parabolic. So I know it's going to be parabolic. Is it fast then slow or slow then fast? Ooh, it's fast, fat stacks, short, slow, short stacks, right? So fast and slow means it goes like this, whoop, and then kind of flat at the top, doesn't it? Now the next section, I got to go down 62.24, but I'm at 46.34, so 46.34 minus, how much? 62.24 equals negative 15.9. So that takes me down to like right there, negative 15.9. And how do I get there? Slow, then fast. So like kind of almost flat and then whoop. And the inflection of these curves, this way versus that way, is probably the most missed thing. So remember the little slow to fast, fast and slow trick. It's very good. Okay, so here we are. Okay, now what's next? We got to go uphill again, 16. Okay, which is going to take us back to, well, I'll tell you where it's going to take us back to. It's going to take us back to 0. Again, there's rounding here, right? Well, why doesn't it take me to 0.1? There's some rounding going on because this is a pin, right? What is the moment at a pin? How much moment is at a pin connection? 0. So I know it has to go back to 0. How does it get there? Well, that's a slope, so it's going to be parabolic, and it's going to be fast then slow. It's going to go like this. Oh, that's not good. Okay, like that. Back to 0. So here I am at 0 at that pin. I know it's got to be 0. And if you don't want to mess up on this rounding, just carry yourself like 4 decimals instead of 2 like I was doing here, right? Because you're going to be off a little bit, right, with rounding. Okay, the next one. Uphill, 3.33. It's not very much, is it? But there's not very much moment there. 3.33 over here, right? There he is, 3.33. And how do I get there? Straight across, next graph, straight slope, right? So that's just a straight line, okay? Ooh, and then there's a moment right there, okay? And the moment is 25. And let's see, we remember our little trick. In the kitchen, the clock is above and the counter is below. So that is a clockwise moment. So that means it's going to go up, doesn't it? So it goes up 25, whoop, to right there. And what's that number? 3.33 plus 25 more, right? This is 14.17 right there. This point right there is going to be 28.33, okay? And then what do we got? Oh, look what we got over here. We got 28.33, 28.34. Again, rounding, right? Rounding. But that's going to go downhill. It's going to take us back to 0. And how do we get there? This is straight across, so next line down, slope, like that. Okay? And there is our graph. Okay? One of the things they may ask you on the test, what is the absolute maximum moment on that beam? What's the biggest bending moment on that beam? Well, now I can look at this graph and I can say the biggest bending moment, 46.34. What's the biggest shear force on that moment? 19. Yep, 19.33 is the biggest shear force. So as a designer, that's what I'm going to have to design for, right? So here's my graph right here. Okay? And that is how you do shear moment diagram. Now, if you're getting stuck on these, you can also flip over to my solid section. There's some more shear moment diagram examples that are exactly the same in the solids course, okay? So if you just need a few more to practice, go look at those, see if they don't help you. Okay, gang, I'll see you back here next time.